The topic of my presentation and PhD studies is satellite laser ranging to low Earth orbiters for orbit validation and determination of global geodetic parameters. With my presentation, I will briefly describe the scientific background of my work. I will next move to the processing chain, and then I will present the main results of my PhD, which consider SLR measurements to LEO satellites in terms of identification of systematic effects affecting SLR residuals, elimination of them, and multi-satellite combination and determination of station coordinates and global geodetic parameters. I will finish my presentation with conclusion and future work plan. Satellite laser ranging is the optical technique based on registration time of flight of the laser signal from station to the satellite. Satellites are equipped with the retroreflectors, which allows to reflect laser pulse into the station. This pulse is reflected to the detector on station, and by having this time of flight, dividing it by 2 and multiply by speed of light, we can achieve the range between station and satellite. Top left figure here, it shows example of spherical geodetic satellites, LAGEOS 1-2 satellites, Etalon satellites, which contributes for the global geodetic observing system in terms of determination of global geodetic parameters, realization of reference frame. Below, we have example of SLR station, which is taking measurements at Graz Observatory. Map shows localization of all SLR stations all over the world. We can notice that most of them are located on the northern hemisphere. SLR measurements to those spherical geodetic satellites are used for the determination of geocenter motion, global scale, station coordinates. As we know, satellites orbit around the center of the mass of the whole Earth system, including Earth, atmosphere, hydrosphere. And when you have stations located all over the world, that data which they provide from different techniques, we can use those data for calculation of center of figure of our Earth, and the difference between those 2 points represent the geocenter motion. Moreover, spherical geodetic satellites contributes for the realization of the international terrestrial reference frames, such as ITRF 2014 or recently published ITRF 2020. Figure shows example of stations from 4 different geodetic techniques, which contributes for the recent ITRF 2020 solution for the Europe region. Moreover, SLR measurements can be used for the determination of gravity field parameters, GM product, or air rotation parameters, for example, length of day parameter, so how fast our Earth is spinning, or the polar motion, the motion of the rotation axis with reference to the celestial intermediate pole. Also, SLR measurements can be used for the verification of general relativity effects. Notwithstanding, SLR provides measurements also to other types of satellites, the main topic of my work, which are active low Earth orbiters, for example, Sentinels, GOES, Swarms, TerraSAR X, JSON satellites, as well as to navigation satellites, for example, Galileo constellation or space debris. LEO satellites have a variety of mission objectives. For example, they are used for the gravity field determination, altimetry measurements, temperature measurements, wind speed, or Earth surface mapping. Moreover, they have different altitudes within the range of over 200 to 2,000 kilometers, shapes, payload, orbit characteristics, all for the particular mission characteristics. Moreover, we have collocation of space geodetic techniques on board LEOs, GNSS, SLR, and also DORIS. Figure shows example of SLR retroreflectors which can be found on LEO satellites, for example, pyramidal retroreflectors, spherical or hemispherical retroreflectors. However, in the case of SLR to LEO satellites, here the main contribution of satellite laser ranging is for their orbit validation, which are derived by GNSS and DORIS precise orbit determination of LEO satellites is in most of cases calculated by using GNSS observations, mostly GPS, by using kinematic and reduced dynamic approach. In the case of kinematic approach, they are based on the epoch-wise discrete position of the satellite by using GNSS observation. It's a geometrical approach, whereas in the case of reduced dynamic approach, here we are based on the equation of motions and modeling of additional forces, such as pseudostochastic parameters or empirical accelerations. When we consider the random and systematic errors, in the case of dynamic approach, here we introduce the model error and minimize the random error. In the case of kinematic orbits, it's the opposite. So there are more random errors than model error. And the reduced dynamic approach, here in this case, we have intermediate level between the two types of errors. Quality of LEO precise orbit determination products have been recently improved in terms of using multi-technique combinations. For example, CNES provides GNSS plus Doris-based orbits of the altimetry satellites. We have improvement of each technique performance. For example, we have a new improvements in constellation of satellites, of navigation satellites, or each technique station performance. Also, geodetic products are improved, for example, static and time-varying gravity fields. We may also notice developments in LEO PhD strategies and procedures, for example, using macro models for modeling of non-gravitational forces, using singular receiving ambiguities, or considering different signals in POD processing. All of above improve consistency between SLAB products and POD products, which is currently at the level of less than 2 or even 1 centimeter or better. Figure shows the example of SLAB validation results from 32 stations, 9 satellites, which shows the consistency between POD and SLA measurements at the level of less than 1 centimeter. When we look at the distribution of LEO of SLA measurements to different types of satellites, we can easily notice that most of them, 76%, consider LEO targets, followed by the spherical geodetic and navigational satellites. Thus, only 30% of them are used for the reference frame realization on determination of global geodetic parameters. In my doctoral thesis, I have tried to verify the research hypothesis, that is, SLA observations to active low Earth orbiters can be employed for the realization of SLR-based reference frames and determination of global geodetic parameters, such as geocenter motion, length of day, and pole coordinates. Main goals are to increase the use of SLA observation to LEO satellites, improve the SLA-based validation of POD products, and develop a methodology and best processing strategy for multi-satellite combination, aiming to determination of global geodetic parameters and reference frame realization. Now I will move to the processing chain, which can be divided into two parts. SLA validation of LEO and SLR to LEO-based combination and determination of parameters. All of these are calculated by using Bernie's GNSS software with additional modifications. First part, consider data acquisition, in which I've used a priori parameters, POD products, Earth orientation parameters, station coordinates, and of course SLA observations. I've used normal point data, and also models and corrections. Then we have preprocessing, so data conversion, extrapolation of coordinates, and orbit integration, and the final processing, which allowed to calculate the SLR residuals, output files, normal equation systems, or calculating of daily corrections, data screening. And when we have normal equation systems, we can move to the next step, so the SLA-based combination and determination of parameters. Here we start with the datum defining stations by stacking of normal equation systems, estimation of station coordinates by using minimum network constraining, and Helmert transformation. It's followed by the combination test, in which I've tested different stacking of normal equation systems in terms of period of observations, choosing different normal equation systems for each satellite, weighting of normal equation systems, and constraining of parameters and the network. And finally, we have estimation of parameters, in which I've calculated station coordinates, pole coordinates, length of the parameter, and geocenter coordinates. Within my study, I've analyzed SLR residuals, and they can be described as observed minus computed range between station and satellite. The observed part consider one-way range with the measurement error, and the computed part considers station and satellite position and modeling systematic effects, for example, SLR RI correction, satellite center of mass correction, relativistic correction, and others. Of course, all of these require proper modeling and high-quality products. Now I will present main results of my PhD work. And I will start with the identification of systematic effects affecting SLR residuals to LEO. I have validated kinematic and reduced dynamic orbits of ghost satellite for the period of about 5 years. And with this analysis, I've compared SLR residuals with indices representing geomagnetic, ionospheric, and solar activity indices. And the figure shows example of such a comparison. We have SLR validation of reduced dynamic and kinematic orbits, and the index representing solar activity. We can notice that since 2011, we have increase of the solar activity, and when we compare it to the validation results, we have increase of the RMS and the correlation with the index of SLR residuals to kinematic orbits, and no increase in the case of reduced dynamic orbits. So the kinematic orbits may reveal sensitivity to the solar activity. Also, parameters of the ghost orbit, which are, we can say, extremely low, circular and synchronous orbits, implies that above the same location, we have 2 types of passes during one day. So one pass may be ascending at the time of near 6 a.m. And the second one, descending pass, this pass is near 6 p.m. And I have analyzed SLR residuals by dividing them into ascending passes and descending passes. And the example of such analysis is in the figure on the left. For example, station, we can see that for some of them, there is the offset of mean values, mean residuals occurring at the station, which may indicate the possibility of occurrence some systematic effects. And when we follow the analysis by analyzing each single satellite pass, we can find some anomalous passes in which for ascending, descending pass, and for 2 types of orbits, we can observe the characteristic change of the residual sign for highly negative to highly positive, which may indicate that here we have the problem, for example, with the systematic errors such as time bias. So by analyzing single satellite passes, we can detect stations which are affected by systematic errors. Then I have also analyzed SLR residual by dividing them into the station which uses particular detector type. Detector is an instrument that used for the detecting input-output laser signal to start-stop time measurements on stations. So this is crucial instrument. Example of one of them is in the figure. And we can list 3 types of detectors: compensated single photon avalanche diode, which can register single to multi photons. We have microchannel plate and photomultiplier tube, both able to register many photons. And in my study, I've analyzed SLR residuals to the swarm orbits with the extension of validation by considering different station groups divided by detector type. Figure shows example of such an analysis for the kinematic orbits. We have SLR residuals with reference to the local time of observation and elongation angle for the PMT, CSPAT, and MCP group. And we can notice that in the case of CSPATs, here there's no dependency between night and daytime tracking, whereas for the MCP and PMT, we can observe 50 mm dependency of the residuals. Now I will move to the second topic, elimination of systematic effects in SLR residuals to LEO. methods for doing reducing the systematic effects in SLR residuals may be range biases, so the constant corrections to modeled ranges, and depending on the approach, we can analyze single pass analysis or maybe longer periods, weekly station satellite corrections, or even 1 year station dependent corrections. Next, we have tropospheric delay modeling, so zenith angle or distance dependent angle correction, which may be as 10-day tropospheric biases or tropospheric biases with horizontal gradients, and time biases. So here we minimize the impact of the timing errors also by analyzing, for example, each satellite pass, longer time periods, or T2L2 experiment. In my work, I focused on the range biases and tropospheric biases in processing. I have calculated the range biases as a station satellite corrections based on 1 year, 1 day period, and I used ESLA measurements to 9 LEO satellites, LAGEOS satellites, LARES, and Galileo constellation. In terms of tropospheric biases, also station satellite dependent values based on the 1 day track period to swarm ABC satellites. Figure shows example of 2 types of corrections, range biases and tropospheric bias median. For the example, 10 stations and different type of satellites depending on the parameter, and also for the tested period of observation. We can notice that this type of corrections are station and satellite specific parameters, which are not stable in time. Range biases are within a range of about 15 plus minus 15 millimeters, depending on station and satellite, whereas in the case of swarm satellites, range and tropospheric corrections are analogical with each other, but tropospheric corrections are within the lower range of about plus minus 8 millimeters, depending on station. And values that I have calculated correspond also to the LAGEOS based estimates. Here, figure presents SLR residuals with reference to the time and with reference to the elevation angle, for example, to stations, residuals of swarm orbits for solution when we do not model any corrections, when we model range biases, and when we model tropospheric bias correction. When we don't have any modeling of systematic effects, we can see the offset of residuals or residual angle dependency. In the case when we use range biases, here we reduce only the offset of residuals, whereas in the case of troposphere biases, here we have reduction of the offset of residuals as well as elevation angle dependency. And I have also tested my approach, so TRP corrections for different precise orbit determination products, IOP kinematic solution, ISIO reduced dynamic solution, and IOP reduced dynamic solution of swarm satellite. And figure shows the histogram of SLR residuals for the solution without any modeling and with tropospheric correction. We can observe that we have in each of analyzed orbit increase the percentage of residuals within the range of plus minus 10 millimeters. So SLR observations are more consistent with different POD solutions when we use this type of correction. And also, it allows for the comparison of the orbit quality between kinematic reduced dynamic orbits provided by different sources. In this case, IOP reduced dynamic solution is the most consistent with the SLR measurements. And the third topic, multi-satellite combination and determination of station coordinates and global geodetic parameters. I have estimated SLR station coordinates, geocenter motion, pole coordinates, and length of day parameter by using various of combinations. For example, I combined only 9 LEO satellites, multi-satellite combination. Here I used 9 LEO satellites, spherical geodetic satellites, and Galileo. I've tested different network constraining with experimental SLR PPP solution in which there were no constraints on the network and only station coordinates were calculated as 3 parameters. Other parameters were fixed to the a priori value. I've also tested weighting of observations, applied annual range biases in the solutions, and compare the results with the Lagios-based solution, IRS products, and SLRF 2014 results. Figure shows station coordinates up, east, north component for over interquadrille ranges of up, east, and north component of over 30 stations. For the solution, when we consider only SLR to Lagios 1-2 satellites, 9 LEO solution, and weighted multi-satellite combination, 3 different types of satellites here were used. And the positioning of all stations for the multi-satellite combinations are at the accuracy level of less than 18 millimeters and 10 millimeters for the up and horizontal components respectively. For core stations, it's even better at the level of 10 and 7 millimeters. Also, I've tested SLR PPP solution. So here only station coordinates were estimated, and we may notice that they allow for positioning at the level of less than 20 millimeters for the up component and less than 15 millimeters for horizontal. Figure below shows formal error of the up component for the solution based on Lagios and multi-satellite combination, and we can notice that formal errors in the combinations are successfully reduced by even 50% to the level of 1 millimeter or even better. And now slide shows geocenter estimates from free solution based on SLR to Lagios, LEO, and weighted multi-satellite combination X, Y, and Z component. We may notice that combinations are consistent with standard Lagios-based solution, and either annual signal of the Z component is recovered. So multi-satellite combination can be used for deriving geocenter motion. Next, pole coordinates are the same, 3 solutions, X and Y pole coordinates. Also, we may notice that multi-satellite combinations are consistent with Lagios products. So also, by this approach, we can use SLR to multi-satellite combinations for deriving polar motion. And a length of day parameter, here we may notice that there is 3 times improvement of LEO only and multi-satellite combination. Here I mean SLR solution RMS of the particular solution. So here length of day parameter can be derived from multi-satellite combinations. And conclusions, processing of SLR observations to active LEO satellites allows assessing the performance of SLR station as well as comparing different LEO POD products and processing methods. I have shown that in some cases kinematic approach may be sensitive to solar activity index or maybe to solar activity, or stations which are equipped with CSPAT detectors gives better observations than other types. SLR observations to LEO satellites can be used for detection, monitoring, and calibration of systematic errors. For example, tropospheric bias corrections reduce both offset of residuals as well as elevation angle dependency of residuals, and allows us for determination of SLR station coordinates and global geodetic parameters, geocenter motion, pole coordinates, length of day parameter. The estimate shows consistency with Lagios-based solution or ITRF products, and a benefit from introducing observations to different types of satellites, not only spherical geodetic. Thus, the main hypothesis of my work can be considered as verified. Future plans, of course, considering other satellites which are equipped with SLR retroreflectors, including new LEOs, for example, Sentinel-6, new spherical geodetic satellites, recently launched LARES-2 satellite, also Stella, GSI, or Starlet. We also hope that Genesis mission will be successful when we have all 4 techniques on board, and it will be great to work with this kind of mission, as well as with navigational constellations. Also, plan is to introduce tropospheric bias correction for the determination of parameters and realization of reference frames. evaluate different types of antennas and receivers on board Clios, and introduce into processing a recently updated reference frame ITRF 2020, and increase the period of analysis. Here you can see the bibliography for this presentation, and thank you for your attention.